Welcome everyone. Today we are going to learn about chemical thermodynamics. Before we study what is actually a chemical thermodynamics, let's know about thermodynamics. Thermodynamics is the branch of physics that deals with the relationships between heat and other forms of energy. In particular, it describes how thermal energy is converted into and from other forms of energy and how it affects matter. So, thermal basically it's heat and dynamic means diverse in nature. Chemical thermodynamics is the study of the interrelation of heat and work with chemical reactions or with physical changes of state within the confines of the law of thermodynamics. While studying chemical thermodynamics, basically we are going to deal with three terms that is system, surroundings, and boundaries, where the chemical reactions are taking place. So, what is a system? A quantity of matter or a region in space chosen for study that is known as your system. The mass or region outside the system is termed as surroundings, whereas the real or imaginary surface that separates the system from its surrounding is known as boundary. For example, say you are performing an experiment, right? To perform an experiment, if you have taken a test tube, so a test tube is setting your boundary, the chemical reactions that is taking place inside the test tube, it is your system, and outside the system, that is outside the test tube, whatever it is there, it is your surrounding. Types of systems depending upon the exchange of energy and exchange of matter. Here we have an example. You can see the picture given over to your right hand side. That is, we have a cup which is filled with coffee or tea. You can see the vapors are coming out. That means it's hot. The next cup, you find a lid is kept on it, and the third one, it is kept in a thermos. So while in the first one you can see it is an open system as exchange of energy and matter both takes place. Whereas in closed system you can check that only exchange of energy is taken place, not exchange of matter. Whereas in the third case, nothing is being exchanged, hence it is known as an isolated system where exchange of energy as well as the exchange of matter do not takes place and which allows the thermals to keep the hot things hot for a longer period of time, a cold thing cold for a longer period of time. Hence, the system is divided into three different types, that is open, closed, and isolated, depending upon the exchange of energy and the matter. Thermodynamic processes as such is classified into four different types depending upon your STP, that is pressure, temperature, volume. uh, a process, a thermodynamic process, is said to be an isobaric process when pressure is kept constant. When constant volume, it is isochoric process. At constant temperature, it is isothermal. And where nothing is constant, that is adiabatic process. Heat is constant, right? So isobaric bar, it is the unit to measure pressure. So isobaric means at constant pressure. Core is to measure the volume. So it is isochoric, isothermal, thermal, which talks about the temperature. So it is your constant temperature, which gives isothermal, and last is the adiabatic process. Next two properties we need to take into considerations, that is intensive and the extensive property. Now, what are intensive properties which do not depend on the amount of matter in a sample? Those kind of properties are known as intensive. They are inner, they are independent. Intensive, independent. Whereas extensive, they are dependent. So, intensive, you can remember the word independent. So we can say intensive properties are independent on the amount of matter in a sample. For example, temperature, boiling, concentration, luster. For example, when we are talking about the temperature, no matter how healthy we are or the weight, right? The body temperature of each and every person remains constant. Even the boiling point of water, if we are talking about that is, though you are going to boil a glass of water, a beaker of water, 1,000 liter of water, yet its boiling point is going to remain 100 degrees Celsius, whereas freezing point is also going to remain 0 degrees Celsius. So as the luster and the concentration, these are independent of on the amount of matter in a sample. Whereas extensive properties depends on how much matter a sample contains, its weight, length, volume, and entropy. Next, a very important law which has been given by Hess. He says that the summation of all the reaction gives the total one, that is heat of any reaction for a specific reaction is equal to the sum of the heats of reactions for any set of reactions, which in sum are equivalent to the overall reactions. For example, here you can say the three different paths are given, that is delta H is equals to delta H1 plus delta H2. Now, where these laws can be applied, so this law is extremely useful to calculate heats of many reactions which do not take place directly. It is useful to find out heats of extremely slow or fast reaction. It is useful to find out the heat of formation, combustion, neutralization, ionization, etc. It helps to calculate the enthalpies of reactants and the products. So this is how Hess law is utilized, and yes, even it is useful to calculate all the numericals based on these concepts. Comes zeroth law of thermodynamics. Basically, we have three different laws of thermodynamics. That is first law, second law, and third law. And zeroth law comes at the end, right? The overall, which determines the thermal equilibrium in the system. Hence, it is coming at the end, and yet it has been named zeroth law of thermodynamics. Zeroth law of thermodynamics states that if two thermodynamic systems are each in thermal equilibrium with a third one, then they are in thermal equilibrium with each other. Accordingly, thermal equilibrium between systems is a transitive relations, right? So, for example, if two systems are in equilibrium with each other, then definitely they are in equilibrium with the third system as well. Here you can see in the example that A is in thermal equilibrium with B, whereas B is in thermal equilibrium with C. Definitely, then A is in thermal equilibrium with C. You can check here how what we are talking about the thermal equilibrium. Right here we have three different systems, that is iron rod, kettle and our hands. Now these three different systems are getting heated. Okay, the kettle is getting the water in a kettle. The water in a kettle, it's getting heated due to the convection current. Whereas iron rod is getting heated by conduction because iron rod itself is getting heated. Even the kettle is getting heated by conduction, but water present in the kettle is getting heated by convection. Whereas our hands are getting heated by the radiations. So three different systems are getting heated by three different means. However, the aim of all these mechanisms is to finally bring these three systems into thermal equilibrium. Limitations of zeroth law is that zeroth law only tells about the equality of temperature. For example, if how do we come to know that whether we are suffering from fever and what is our body temperature? So we do take use of the clinical thermometer. Now, when we clinical thermometer comes in contact with our body, the heat transferred from our body to the clinical thermometer and the temperature of our body is noted down in the clinical thermometer. So this is the way how the heat is being transferred. Hence, so zeroth law only talks about the equality of temperature, but it does not give any clue how the heat is being transferred. It does not speak anything about the energy conversion. It only helps in the calibration of thermometer, whereas the first law tells about energy conversion. So first law of thermodynamics says that energy can neither be created nor be destroyed. Therefore, the total energy of the universe remains constant. Energy can, however, be converted from one form to another or transferred from a system to the surroundings or vice versa. So, first law of thermodynamics is nothing but the law of conservation of energy that we have already learned in your lower grades. Spontaneous process. What is a spontaneous process? The process that occurs on its own without any outside intervention is called a spontaneous process. Here is the example given on your right hand side. We have a bulb that is B. Two bulbs A and B. Bulb B is filled with a volume, a gas, and it has been two bulbs are connected with a stopcock. Now once the stopcock is open, the gas present in the bulb B is going to get transferred to the bulb A till the volume of the gas becomes similar in both the bulbs. So that is spontaneous. Now to get back the original condition, the reverse is not at all possible on its own. So the gas in vessel B will spontaneously effuse into vessel A, but once the gas in both the vessels is same, it will not spontaneously get into the another one. Again, one more example that processes that are spontaneous in one direction are non-spontaneous in the reverse direction. Here you can see an iron nail, a fresh iron nail gets rust on its own, but from rust, the rust is not being removed on its own. To remove the rust, we need sandpaper to rub on it. Hence, we can say the processes that are spontaneous at one temperature may be non-spontaneous at other temperature. For example, melting of ice into water, that is, the temperature should be greater than 0 degrees C. Conversion of water into ice has to be less than 0 degrees C. Reversible process. In a reversible process, the system changes in such a way that the system and surroundings can be put back in their original states by exactly reversing the process. Changes are infinitesimally small in a reversible process. Irreversible process cannot be undone by exactly reversing the change to the system. All spontaneous processes are irreversible. As we have already seen the examples of spontaneous process, that is rusting of iron, melting of ice, freezing of water. These all are the spontaneous process which are irreversible. All real processes are irreversible. Next term comes entropy. Now, what is entropy? Entropy is a term coined by Rudolf Clausius in the 19th century. Clausius was convinced of the significance of the ratio of heat delivered and the temperature at which it is delivered. Mathematically, entropy is represented as Q upon T. Now, what is Q? Q is the heat transferred to the system or by the system at a particular temperature given. Entropy can be thought of as a measure of the randomness of a system. More the randomness of a system, more will be the entropy. Hence, it is related to the various modes of motions in molecule. So we can define entropy as the disordered or randomness of the molecules present in a given system. Like total energy E and enthalpy H, entropy is also a state function. So what is a state function? The variables that do not depend upon the path, but it depends only upon the destination, is known as state function. Therefore, delta S, that is change in entropy. Entropy is denoted by capital X. Therefore, change in entropy is equals to S final minus S initial. For a process occurring at constant temperature means the isothermal process. So, entropy can be measured during isothermal process by the formula, that is change in entropy is equals to Q reversible upon capital T, where Q reversible is equals to the heat that is transferred when the process is carried out reversibly at a constant temperature. Temperature is equals to temperature in Kelvin. Second law of thermodynamics is related to the entropy. First law of thermodynamics related to the law of conservation of energy. Zeroth law of thermodynamics talked about the thermal equilibrium. Now we have second law of thermodynamics, which is related to the entropy. Hence, second law of thermodynamics is stated as the entropy of the universe does not change for reversible processes and increases for spontaneous processes. Therefore, we can represent change in entropy is equals to change in entropy with system and surrounding, that is equal to 0 for a reversible process. Now, for irreversible or spontaneous or real process, the change in entropy of the universe should be equal to change in entropy of the system and surrounding, that is positive, greater than 0. You can't break even reversible or ideal process, which is equals to 0, whereas irreversible process, your change in entropy of the universe should be positive. The entropy of the universe increases, but entropy can decrease for individual systems. Entropy on the molecular scale. Ludwig Boltzmann described the concept of the entropy on the molecular level. You can see when the temperature of a molecule is increased, which all process takes place, vibration and then rotational and translational motions are taking place. Temperature, what is temperature? Temperature is a measure of the average kinetic energy of the molecules in a sample. Molecules exhibit several types of motions, that is, translation motion, rotational motion, and vibrational motions. So, what is a translation motion? Movement of the entire molecule from one place to another is called as translational motion, whereas periodic motion of atoms within a molecule is called a vibrational motion. And the last is rotation of the molecule on about an axis or rotation about sigma bonds is termed as rotational motion. Boltzmann envisioned the motion of a sample of molecules at a particular instant in time. This would be akin to taking a snapshot of all the molecules. He referred to this sampling as a microstate of the thermodynamic system. Each thermodynamic state has a specific number of microstates W associated with it. Entropy on the molecular scale, Boltzmann envisioned the motion of a sample of molecules at a particular instant in time. This would be key to taking a snapshot of all the molecules. He referred to the sampling as a microstate of the thermodynamic system. Each thermodynamic state has a specific number of microstates W associated with it. Entropy is represented as capital S is equals to K into natural log W, where K is the Boltzmann constant and its value is 1.38 into 10 raised to minus 23 joule per Kelvin. More particles implies more states, more entropy. Higher temperature, more entropy. Less structure, gas versus solid. So gas is having more entropy. The number of microstates and therefore the entropy tends to increase with increase in temperature, volume, and number of independently moving molecules. Entropy and physical states. Entropy increases with the freedom of motion of molecules. Therefore, entropy of gaseous state is greater than the liquid and it's greater than the solid state. Solutions, dissolution of a solid. Ions have more entropy, that is more states, but some water molecules have less entropy. They are grouped around ions. Usually, there is an overall increase in entropy. The exception is very highly charged ions that make a lot of water molecules align around them. Entropy changes. In general, entropy increases when gases are formed from liquids and solids. Liquids or solutions are formed from solids. Number of gas molecule increases. Number of moles increases. Third law of entropy says the entropy of a pure crystalline substance at absolutely zero temperature is zero. I repeat, the entropy of a pure crystalline substance at absolute zero temperature is zero. Therefore, we can say S is equals to K into natural log W, which is equals to K natural log 1 is equals to 0, work done, right? W by W, it is equals to 1. The entropy of a pure crystalline substance is 0. So hence you can see over here that with increase in temperature, right, the melting and boiling point of liquid and gas. Standard entropies talks about the molar entropy values of substance in their standard states. Don't worry, we don't have to memorize these values. This will be given to us for solving the numericals. Standard entropies tend to increase with increasing molar mass. Larger and more complex molecules have greater entropies. Entropy changes for a reaction can be calculated the same way we used for calculating change in enthalpy. So change in entropy is equals to summation of the standard entropy of the reactants minus the summation of the standard entropy of the products. This is for the practical uses for surrounding and system. Change in entropy in surrounding is equals to minus Q system upon T. Now why minus Q? Whenever the heat is transferred by the system to the surrounding, at that moment Q is negative. So heat that flows into or out of the system also changes the entropy of the surroundings. Now at constant pressure, Q system is simply change in enthalpy for the system. So we can even represent delta S surrounding is equals to minus delta H0 upon capital T. Entropy change in the universe. The universe is composed of the system and the surrounding, as we have seen in the beginning of the chapter. Therefore, delta S universe is equals to delta S system plus delta S surroundings. For spontaneous process, change in entropy in the universe is always greater than zero. That means it is positive. So this is how we can represent the change in entropy in the universe. Where T delta S represent Gibbs free energy. Now, just we have a relation between the Gibbs free energy and the change in enthalpy and the surrounding, entropy. So here you can see when change in entropy is positive, Gibbs free energy will be negative. So this is how it is defined, and this is how for spontaneous process change in entropy has to be positive, whereas change in Gibbs free energy will be negative. If change in Gibbs free energy is negative, the forward reaction is spontaneous. If it is zero, it is attaining an equilibrium. If it is positive, the reaction is spontaneous in the reverse direction. Standard free energy changes comes across. Standard free energies of formation are analogous to standard enthalpies of formation. This is the key equations that we are going to take care of, which is useful for solving number of numericals that are given in your textbook. This is the equation showing the relationship between the temperature and the change in Gibbs free energy. We assume standard entropy and standard change in enthalpy are independent of temperature. Two parts of the free energy equation. One is enthalpy and one other is entropy. The temperature dependence of free energy comes from the entropy term, and this is a very important table which is going to help you to answer number of MCQs and even your competitive examinations questions. By knowing the sign positive or negative of change in entropy and enthalpy, we can get sign of change in free energy and determine if a reaction is spontaneous or not. Hence, we have the relation with respect to the real gas constant. This is how the Gibbs free energy shows the changes, whether it is attending a forward spontaneous reaction, equilibrium, or the reverse reaction. Thank you. Have a nice day.